He's the man, he's the myth, he's the legend, he's the scientist with all the answers to all the questions. It's time for another episode of Alex's Science Corner.
Oh, thank you. No, please, thank you.
It's been a while since we've done a true Alex's Science Corner.
Holiday season tends to disrupt things, but we've got this is episode 101 that's going to go up on the YouTube channel. So
what's going on in the wide world of science, my friend?
So the first story is scientists have created the coldest chemical reaction that has ever been done. And now they're not doing it just to be cold. Chemical reactions happen very fast. They can happen in a picosecond. Now, what a picosecond is think of 1 second, then put a point before it, and then 12 zeros, and then a 1. That's a picosecond. So it's 0.000, 12 zeros, and a 1.
Flash.
Really, really fast. So what these researchers were able to do is they were able to cool this reaction process down to the point it's just above 0 degrees Kelvin, which is at 0 degrees Kelvin, there's no molecular motion. But they cooled it to just above 0 degrees Kelvin.
So if they froze your hand, it would just fall off.
Oh, well, yeah. It'd
crumble, right?
Yeah, because, there's no reaction. At 0 degrees Kelvin, there is no molecular motion. And so, we talk about putting stuff in liquid nitrogen or whatever. That's super cold. Yeah, that's not cold compared to 0 degrees.
That's kids' play.
Yeah, that's kids' play. So they cooled this reaction down, and using laser photometry, they're now able to slow down the reaction and see what's happening in that reaction. And the reaction is now slowed down to 1/1,000,000th of a second instead of 1 picosecond.
Now, why are we doing this?
So that we can see what happens when two chemicals combine or when a chemical breaks apart. We can see that process. And if we see that process, we can figure out why it's happening and see ways we can see things that we might be able to try to adjust that process. More we understand about how chemical reactions work, the more we can do to deal or modify or improve the processes we use to do those chemical reactions. Because chemistry is in everything.
Sure.
And so knowing how we do something, knowing how it reacts, finding a better way to do it or a different way of doing it always is better.
Cooking is chemistry, right?
Exactly. They have a lot of reactions, like the Maillard reaction is the browning of whatever you're cooking on a grill or in frying. The browning that you get from that, that's called the Maillard reaction. There's a lot of reactions in chemistry.
So your hash browns,
yes, exactly,
are a Maillard reaction,
right? But again, this is the coldest. They've gotten it to 0.05 degrees Kelvin, which is a very low number. And they're able to slow down the reaction so that now they can watch the reaction happening, the chemical reaction. So that's big news in chemistry. It is, again, it's one of those kind of detailed things that we as everyday people are not going to be doing it on our everyday scale, but it's a new way of seeing the universe.
And we wouldn't know it unless you just told us.
Well, the guys who did it would know about it.
Sure,
so
of course.
Letting everybody else know what they did.
Right. That came from a chemistry journal, I presume, right?
Yes. The second one is December 4th. NASA published, researchers have published 4 different papers from the Parker Solar Probe. Now, the Parker Solar Probe is a probe that we launched toward the sun. It is orbiting the sun very closely. It's entering the outer solar atmosphere, which is the corona. It is moving at 430,000 miles an hour when it passes by the sun.
What kind of temperatures is it enduring at
the
moment?
It is very hot. When it has to go, It is very
How
big.
hot is it?
You know what? They don't even have numbers for that.
Really?
Yeah.
Wow.
There's a sun shield, and when it's passing by the sun shield always has to be pointing. It can't use any cameras, and all of the instruments it has are in the shadow of the shield, pointing outside to the sides.
So hot
they
enough to fry an egg.
Oh, yeah. Well, I'm going to explain how hot it is in a little bit. But again, it is incredibly hot, and the sun shield is protecting it. And it's going to have, this is right now done its second orbit. It's starting its third orbit. And it's going to do about 10 more orbits around the sun.
Does it get closer as it's orbiting?
It is getting closer for this orbit because part of the orbit involves gravitational interaction with Venus, and that is making it go a little bit lower.
So it will eventually just go right in.
Well, it's not even going to go
toast.
in. It's going to get toasted before then.
Okay.
Because what will happen is it has to use fuel to keep the sun shield pointed at the sun as it's going around. And at a certain point, it's going to run out of fuel. And so that when it runs out of fuel, it's not going to be able to keep the sun shield pointed at the sun. At that point, the satellites could get ripped apart.
They were able to keep enough fuel to launch it, and it has enough fuel.
Well, that's, again, all you're doing is just doing enough to keep it rotating. So that the sun shield stays pointed. That's a separate amount of fuel than the rocket that launched it.
Okay.
Right. Don't get me wrong. The rocket that launched it was also the largest rocket, except for the Saturn V, that we've ever launched. Which is funny because we're sending it closer to the sun, but it had to be a very large rocket to do that because of the way it had to do the orbital interactions so that it could get into this orbit.
Okay.
So far, like I said, in 2 orbits so far, they've discovered a whole bunch of different things. For example, the magnetic solar wind has kinks in it. From Earth, we've only seen like this magnetic solar wind that comes out and comes straight at us, but closer in, it's lumpy, it's wavy, there's stuff flying off of the sun in all directions. There's a lot of material that's coming off the sun, but we don't see a lot of it because by the time it reaches us, it's so weak from those particular small lumps.
Just a question: is the core of the sun solid, or is it? Oh, we don't know.
The core of the sun is where the fusion is happening. Let me back up. Let me finish up the story, and I'll go back.
Okay, you don't
because
you don't
this is kind of important to describe all this too. I will describe one other bit, and then I'll go talking about the sun a little bit. There's a thing about dust also that they're learning. They expected that dust is supposed to disappear as it gets closer to the sun. The solar system is filled with dust. But about 7 million miles away from the sun, the dust disappears. And that's because the sun is so hot that the dust begins to evaporate, that the dust cannot hold together as dust anymore because it's just being ripped apart by the heat. There's massive amounts of particles that come out from the sun, energized and magnetic particles that come out from the sun. But dust cannot hold together that close to the sun. So the closer you get to the sun, the less dust you see because it evaporates. Just like water evaporates off of a hot skillet. This is the dust, whatever the dust particles are evaporating that close.
Okay.
So that was one of the really big stories of how, asking about how hot it is. That's how hot it is. Dust cannot form that close.
Within 7 million miles.
Yeah. Now, the way the sun works is in the center of the sun, there's so much pressure and material and heat from that pressure. This is where fusion happens. Hydrogen molecules are being forced together. When the hydrogen molecules are forced together, it produces energy. That's fusion. That's like, nuclear bomb, but we're talking about the sun, which is doing that all the time. That energy is putting out enough force and light that it's pushing the rest of the material out, which is giving the sun its size and all the heat and energy that's radiating out from it. So in the center, is it solid? Yeah, you could kind of say it is, but it's because it's so dense and hot in that center that it's dense enough that hydrogen molecules are fusing together. Eventually, hydrogen molecules will run out, and then the helium that the hydrogen molecules are forming will start fusing together, and then the sun will expand out farther than that. And then when it stops fusing helium, then it'll start fusing the next level of molecules until it starts trying to fuse iron. And then iron, you're not going to get energy from fusing iron, so the sun will collapse into a white dwarf.
So that's when it's all over.
Yeah, 5 billion years from now.
5 billion years from now. Okay, so we're all right.
Yeah, you and I. Yeah, we've got other issues to deal with.
You don't have to worry about it right now. Okay.
You're saying, is it solid? In a way, it is incredibly solid because the hydrogen is so close together that it's being forced to fuse. That's how dense it is in the sun. That's not as dense as it will be when it becomes a white dwarf, but that's how dense it is right now.
Okay. Anything else to add?
Do you have any questions about this?
Well, what's this whole thing with massive solar winds or solar storms, and how does that affect us?
They can affect us in a lot of different ways. Solar storms, there are things called coronal mass ejections in solar storms. Solar storms are energetic particles come out from the sun all the time. If a big wave of them passes over the Earth, they can disrupt satellites because these energetic particles can disrupt electronics. So satellites could potentially be knocked out. If the storm or the coronal mass ejection is strong enough, it can disrupt electronics and power lines in the world. So because what happens is your power transmission lines, any kind of electronics, their wires become antennas, and so they'll get this massive charge, and they could start frying electronics.
Could it fry the grid? I mean,
it could theoretically. A large enough solar mass ejection that hits the Earth could fry
everything.
Grid. Yeah, it could knock out the grid for a few months.
Wow!
One blast, and that's one of the biggest concerns that researchers are having with this alien invasion. No, solar mass ejection. Blast, because the people that run the electrical grid, they're not putting a lot of time and effort to having that kind of protection in the grid, simply because that stuff is expensive.
And what are the chances of it happening?
Well, eventually it will happen. It's just what is the chance? On a day-to-day basis, it's not a very strong chance, but it's eventually the dice are going to come up that way.
And you'll get hit by lightning.
Yeah. I mean, your chance of getting hit by lightning are small. You got to remember also, we are a speck of dust that is really far away. So from the sun, it doesn't look like it when you look at a drawing, but we're really far away. And a lot of these mass ejections they're aimed out in open space, and there's a lot of them going on, but we're a little tiny dot, and getting hit by any particular coronal mass ejection is really minor. But if we did get hit by one, it'd be a serious event.
Okay.
So, we got hit by one in the late 1800s, and it disrupted the power grid at that time. But there wasn't much of a power grid, and most of the country wasn't electrified, so that wasn't as big a deal as it would be nowadays.
They probably didn't have any idea what happened, did they?
No, well, they didn't know at that time, but, researchers after the fact was like, it's like there's this big, massive disruption, all the electronics around the world. There wasn't much, but we saw it happen. They recorded it, and then it's like researchers went back after the fact and this was probably a mass ejection, coronal mass ejection that caused that.
Okay.
So,
all right, we're gonna wrap it up, and if folks out there want to chime in, I'm sure Alex will take your questions about these two stories or anything else related, science related, of course. You can call it 203-837-9924.